Okay, let's take roll. And okay, answer to your names, please. Barat, Bassi, Burke, Kane, Dunlap, Gallegos, Head, Irvin, Medina, Kylie, Ina, Manuel, Denisi, Marcier, he's here. Olano, Richardson, Sieg, here. Hillman, here. Venture Pagada, here. Lefland, and Wright. And Miss Dunlap just walked in. All right. So I don't know if you guys have seen the announcement I posted. What I've decided to do, and this is basically to make things a bit easier on you. I've decided to postpone the test schedule for tomorrow to Monday. Also, as I said to some of your fellow students earlier, I'm trying to arrange for us to, if you so choose, I can set some time aside over the weekend in order to, answer any questions or if you need any explanation of anything. And this would have to be totally online on Zoom. And the only days I'll be available for this purpose would be on Friday and Sunday, not Saturday. All right. It's all a matter of deciding what time slot you guys would find more convenient for us to meet so that you can get the help that you need. All right. So I was thinking that at the end of class or close to the end of class, we can decide on that when more of your fellow students come so that they can have a say as to when would be a good time for us to meet over the weekend. So you can keep that in mind while we're going through today's class, all right? Oh, I see Kane just stepped in. All right, so with that said, let's talk about acid-base properties of salts. Now, you may have learned in General Chemistry 1 or high school chemistry that a salt is a substance which is produced when a base reacts with an acid, all right? We call that the neutralization reaction, right? Acid plus base gives you a salt and water. And of course, the formula for the salt is based on the formulas for the acid and the base that are involved in this reaction, right? And you may have been taught that the reason why it's called a neutralization reaction is because the products are neutral. We know that water is neutral, and the presumption is that the salt that is produced is neutral. What you're about to learn now is that that is not always true. The salt is not always neutral. The salt itself can have an effect on the aqueous environment such that it favors the formation of protons or hydroxide ions. In other words, it can make the resulting solution acidic or basic, right? So what we're going to look at here is how can we make that prediction? How can we predict that a salt which is dissolved in water will result in a solution being either neutral, acidic, or basic, all right? So first we're going to talk about the type of salts that will produce a neutral solution, all right? And basically salts which contain an alkaline metal or alkaline earth metal, excepting beryllium 2+, and the conjugate base of a strong acid like chloride, bromide, and nitrate, and so on. So any salt that fits this description here will be neutral in terms of the solution that it forms, all right? And the main reason why, the main reason why is because let's say we take sodium chloride. In fact, let me see if I have that here. Right, sodium chloride, right, perfect example. So if you add sodium chloride to water, it will dissociate, right? And in order for us to make predictions as to the effect that it would have on the pH of the solution, you have to see whether or not the different ions will actually interact with water to result in either an increase in the pH or a decrease in the pH, right? And it turns out that sodium, the ion itself, basically just stays stable in water. It does not react with water at all. All right. So therefore, the sodium will have no effect on the outcome in terms of pH, right? So no effect as far as the sodium is concerned. And the same is true for the chloride, no effect, right? Because the chloride is also very stable, right? So basically, whenever you have sodium and chloride ions present in the aqueous solution, the pH will neither increase or decrease. It will remain 7, all right? Pure water is 7. So when you add sodium chloride to it, the pH remains 7, right? And this is true, as stated up here. If the conjugate base that we have here is from a strong acid, Cl minus is the conjugate base of hydrochloric acid. And we all know that hydrochloric acid is a strong acid. So therefore, the chloride is a very weak base, so weak that it does not affect the water. And the sodium here is from the alkali metal group, or group 1A. Sodium ions will have no effect on the water, and therefore the pH of sodium chloride will be 7, all right? So that's as far as neutral solutions are concerned. Now, for basic solutions, these are formed when the salt that is added to the water comes from a strong base and a weak acid, all right? So an example of this would be sodium acetate, and there's an error here. Please make a note of this. There should be no H here. So that's the sodium acetate. When you add that to water, it will dissociate. As I said before, upon dissociation, what you have to look at is the effect that the ions in the aqueous solution will have in the water. As we said before, the sodium ion has no effect, right? So there will be no change in the pH as a result of the sodium ion present in the aqueous solution. However, in the case of the acetate ion, which is the conjugate base of a weak acid, it will have an effect on the pH of the solution. Now, how will it affect the pH of the solution? Basically, this is what's going to happen. The acetate ion will react with water to form acetic acid and, very importantly, the hydroxide ion. So therefore, there will be an increase in the hydroxide ions present in the solution. And therefore, that means that the solution will be basic. In other words, the pH of this solution will be greater than 7, all right? So just to recap, when it comes to salts that are derived from a strong base and a weak acid, right, such as sodium acetate, this is derived from sodium hydroxide and acetic acid, which is a weak acid. Sodium hydroxide is a strong base. What will happen is that it's going to dissociate. The sodium ion that is formed will not have any effect on the water, but the acetate will react with the water, as seen here, and you're going to end up with the acetic acid being formed, but also the hydroxide ion. So therefore, as a result of the increase in the concentration of the hydroxide ion, the pH of the solution would increase, all right? So that's basically what will happen if you add a salt from a strong acid, a strong base and a weak acid, added to water, the solution will be basic. Okay, then we get to acidic solutions. And in acidic solutions from salts, these are formed from salts that are derived from a strong acid and a weak base, all right? So an example of this would be ammonium chloride, right? The ammonium ion is derived from a weak base, and the chloride is the conjugate base of a strong acid. So what's going to happen is that the ammonium chloride, we're going to use this as an example, when it is added to water, will dissociate to form ammonium ions and the chloride ion. Now, the chloride ion, as we said earlier, will have no effect on the solution. So no effect, because the chloride ion is very stable. It's formed from a very strong acid. So therefore, the chloride ion will have no effect on the pH. The ammonium ion, on the other hand, will have an effect on the pH, because what's going to happen is that the ammonium ion itself will dissociate to form NH3, and most importantly, the hydrogen ion, right? So because there's an increase in the concentration of the hydrogen ion upon the reaction of the ammonium to form ammonia and H+, the pH of the solution will decrease. In other words, the solution will become more acidic, all right? Now, this is true also if you're dealing with salts which have a highly charged small metal cation, Basically what they're talking about here, there's a term in chemistry we talk about what is called charge density, right? So basically, if the ion has a very high charge density, in other words, it's small and has a relatively large charge, then basically what you'll find is that these solutions tend to be acidic as well, right? Along with the conjugate base of a strong acid is combined with, right? So those type of compounds will also, when added to water, will produce an acidic solution, all right? So an example of this would be this ion here, which is the aluminum ion, aluminum 3+ ion, which is surrounded by 6 water molecules, right? And what happens is that because the aluminum ion is so small and highly charged, it is going to basically pull electrons from one of the hydrogens here to form this. So therefore, as a result of the formation of the H+ here, the formation of the H+ here, the solution will have an increase in the concentration of H+, and therefore, as a result, the solution will be acidic. Okay, so that's basically what happens when certain ionic compounds form acidic solutions, all right? So this is just going further into what happens in detail as far as the example I showed you. So this is the ion I showed you before. This is what we call the hydrated aluminum ion. And the reason why we consider it such is because you have the aluminum 3+ ion here, and it is bonded to 4 water molecules to obtain an octahedral shape. So what happens is that the aluminum ion, because it's highly charged, will pull electrons away from this oxygen here, and at the same time, electrons will be pulled away, electrons will be pulled away from this hydrogen, by this oxygen. So basically, you have a pull of electrons here, so the electrons in this bond here will be closer to the aluminum, and the oxygen here will end up with a reduced negative charge, which would make this attractive for the pair of electrons being shared between this oxygen and this hydrogen. So what that means is that this hydrogen here will have a relatively high positive charge and will attract the negative end of a water molecule. So what's going to happen is that this oxygen here from a separate water molecule, which is not a part of the octahedral structure, will donate its pair of electrons here. The hydrogen here will be transferred to this oxygen, and you're going to end up with the hydronium ion, which results in an increased acidity of the solution. A negative charge, which is shown right here, will remain on the oxygen, right? So therefore, as a result of the increase in the concentration of the hydronium ion or H+ ion, then the resulting solution is going to be acidic, all right? Okay, so just to summarize what we just discussed in terms of the acid-base properties of salts, if you have a cation from a strong base in the salt and then an ion from a strong acid, such as these examples right here, there will be no reaction between the ions and water, so therefore the solution will be neutral approximately. It might differ a bit from 7. If the cation is from a strong base and the anion is from a strong acid, such as the example shown here, what will happen is that the resulting solution will be basic, which means that the pH will be 7 or greater than 7. And the reason why that happens is because the anion, which is formed from the weak acid, will be reacting with the water to produce hydroxide ions. In the case of a situation where the cation is from a weak base and the anion is from a strong acid, the pH will be less than 7. These are 2 examples. And the reason why that is the case is because the cation itself will undergo reaction with water to form H+ ions. And then now, what if, we didn't talk about this particular situation earlier, but what if the cation is from a weak base and the anion is from a weak acid? And the answer is, it depends. And what does it depend on? It depends on whether or not the Ka value for the acid is greater or less than the Kb value for the base, all right? So for example, well, as stated here, if Kb is less than Ka, then the solution will be acidic, right? So the pH will be 7. If Kb is equal to Ka, then the pH will be approximately 7. if Kb is greater than Ka, then the solution will be basic, and therefore the pH will be greater than 7. All right. And these are just a couple of examples. So, for example, if we take ammonium nitrate, right, the ammonium part would be the acid, and the nitrite, not nitrate, would be the basic part, right? So basically what you have to do is look at the Kb for this and look at the Ka for this, and the one that is greater will determine the resulting outcome in terms of the pH of the solution. All right, so that's basically what that is all about. And we talked about this just now. If you have a small highly charged cation and an anion from a strong acid, then basically the pH would be less than 7, which means that the solution will be acidic. And I explained the reason why that is the case. Now up here, basically this is reiterating what I said here. If Kb for the anion is greater than Ka for the cation, then the solution will be basic. If Kb for the anion is less than the Ka for the cation, then the solution will be acidic. So that's what I was talking about right here. All right, it all depends on comparing the Ka to Kb and which one will be greater, right? And also, if Kb is approximately equal to Ka, then the solution will be neutral. All right, so that's as far as acid-base properties are concerned. This is basically showing you the type of acid-base properties displayed by the oxides of different elements relative to their positions in the periodic table. And what you'll find is that those oxides of elements in groups 1A and 2A, with the exception of hydrogen, of course, they tend to be basic, right? And that is basically shown by this green color here, represents all the particular compounds that will be basic. If you have a nonmetal bonded to oxygen in a compound, then that compound tends to be acidic. There are some exceptions, but they tend to be acidic, and that is shown over here on this side. So compounds like diboron, trioxide, carbon dioxide, dinitrogen, pentoxide, and so on. Those compounds, as you can see here, blue represents acidic oxide. So these compounds here are acidic. And then we have what are known as amphoteric oxides. Now, amphoteric oxides, the term amphoteric is that means that compounds can display both acidic and basic properties, right? So compounds like beryllium oxide, aluminum oxide, and so on, these are all amphoteric oxides. In some cases, they react as a base. In other cases, they react as an acid. So they're kind of in between in terms of their properties, basic and acidic oxides. So here we have an example of an acidic oxide. The thing about acidic oxides is that when they're added to water, they form an acidic solution. So for example, carbon dioxide, when dissolved in water, produces carbonic acid, and dinitrogen pentoxide, when added to water, produces nitric acid. So that's basically how non-metallic oxides, for the most part, behaves, right? Okay, now, we talked about 2 definitions of acids, all right? We talked about the Arrhenius definition, and we talked about the Bronsted definition, right? And we did similar definitions for bases. So just focusing on acids here, just to remind you, an Arrhenius acid is a substance which, when added to water, produces H+ ions, right? A Bronsted acid is basically a compound which donates a proton to a base, all right? So they don't actually contradict each other, excepting that you can have compounds which are considered to be Bronsted acids that are not Arrhenius acids, all right? In fact, the Arrhenius acid definition is based on how the compound behaves when you add it to water. Bronsted definitions of acid, water is not necessary as a part of that definition. But there is a third definition of acids that I'm going to introduce to you now, and that definition is the Lewis definition. And basically what Lewis definition says is that an acid is a substance that can accept a pair of electrons from another substance. And while we're at it, we can talk about a Lewis base, which is a substance which can donate a pair of electrons to another substance, all right? So those are 2 new additional definitions of acids and bases. So a Lewis acid will accept electron pairs, and Lewis base will donate electron pairs, all right? So just to give you an example of H plus combining with OH minus. So basically, you're going to have the donation of an electron pair from the hydroxide to the H plus, and that forms a bond between the H and the oxygen, and that gives you, of course, water. So therefore, according to the Lewis definition, the H plus, because it accepts electron pairs, is considered to be an acid, and the hydroxide, because it donates an electron pair, is considered to be a base, right? So again, this definition does not contradict either Arrhenius or Bronsted, excepting that there are some instances where you can have an acid, which is a Lewis acid, and a base, which is a Lewis base, which would not be the case based on the Arrhenius or Bronsted definition. Here's another example. Again, you have a lone pair of electrons here, which would be donated to the H plus. As a result, you're going to have the formation of a bond right here. So you're going to end up with your product here. And of course, this again would be the Lewis acid. This again would be the Lewis base, based on the definitions that we talked about above. All right. Now, let's look at this example. So this is an example of an acid-base reaction according to Lewis, which would not be the case if you're talking about the Arrhenius or if you're talking about the Bronsted definition, right? So in this particular case, what will happen is that this pair of electrons will be donated to the boron, right? Now, this can happen because the boron basically is electron deficient. And the reason why we consider it to be electron deficient is because it has only 6 electrons in its outer shell, or 3 pairs, right? Remember, for the elements in periods 2 and 3, when they form compounds, especially the non-metallic elements, they tend to form an octet, right? They need 8 electrons on their outer shell. As you can see in the structure, boron has 6 electrons on its outer shell. So therefore, it's considered to be electron deficient and therefore will readily accept an electron pair from the nitrogen from the ammonia. So you're going to have a bond being formed between the nitrogen and the boron, which is this product right here. So based on the Lewis definition, this would be the acid and this would be the base, right? Strictly by the definition put forward by Lewis. However, if you think about it in terms of the Bronsted definition, that would not be the case, right? Because remember, the Bronsted definition requires a transfer of hydrogen ions. There are no hydrogen ions being transferred in this reaction right here. So according to Bronsted, this would not be an acid-base reaction. But according to Lewis, this would be an acid-base reaction because all that is required for the Lewis definition is the donation of an electron pair from one species to the other, all right? So as stated here, there are no protons donated or accepted. So therefore, this would not be an acid-base reaction according to Bronsted, all right? Okay, finally, some applications of what we have just learned in this chapter. I'm quite sure you're familiar with antacids, right? That supposedly deals with heartburn. Heartburn has nothing to do with the heart, has to do with excess acid in the stomach, right? As you should know from your biology courses, among the contents that naturally appear in the stomach is hydrochloric acid, which aids in the digestion of, usually, if I remember correctly, fats and so on. So basically, if there's excess acid, eventually you have what is known as acid reflux, where some of the contents of the stomach finds its way up into your esophagus and can cause some irritation and so on. So basically, we have some preparations here that are commercially available, which basically reduces the amount of acid that is present in the stomach if you suffer from that. So what they all have in common is that they're all basic. They will react with the excess acid to produce some compounds or products that are neutral. So one example of this would be Alka-Seltzer, for example, which contains, among other things, sodium bicarbonate. So therefore, what will happen is that sodium bicarbonate will react with acid in the stomach, and these are the products. You're going to end up with sodium chloride, water, and carbon dioxide. And basically, it's the same thing for the others that you see here. So these are all examples of antacids, which basically contain some active basic ingredients, such as, for example, milk of magnesia. The active ingredient is magnesium hydroxide, and this is the reaction when the magnesium hydroxide reacts with the hydrochloric acid from your stomach, and you're going to end up with your products, which are pretty much harmless, all right? So that's basically one application of the use of acids to reduce excess acid in your stomach. Okay, so that's basically it for this chapter. So let's go to the assignments, because I think there are some questions. Well, I know there are some questions I told you guys to that was assignment 3, right? I'm sorry, assignment 4. In the meantime, let's see who came in late. Okay, is Barat here? Here. Sassy? Here. Olano? Richardson?
Here.
And Wright? Here. Okay, so where did we stop?
The last question we did was question 10.
Question
10.
10? Okay, so we did both A and B?
Yes.
Okay. All right, so if I remember correctly, I told you guys to try 11 on your own. Any difficulty with it? Do I need to explain anything? 11A, I think, is very similar to a previous question we did earlier. 11A is similar to I think it's similar to 9. Did we do 9?
No.
Or did I tell you guys to try 9 on your own?
I chose to try.
Okay. Let me scroll up here and see. All right. So, do we need to do 9 or? Okay. All right. So for 9, let's see what you guys did. It says compare the pH of the following. So basically, you're going to calculate the pH of both solutions. And of course, remember what I said, when it comes to these questions, the first thing you ask yourself is whether or not the acids involved are strong or weak. And remember, there are 6 acids that you need to memorize as strong acids, all right? Okay, and then any other acid that you may encounter is more than likely weak. All right, so we have 0.10 M nitric acid and we have 0.10 M nitrous acid. So the question is, okay, let's start off with the 0.10 M nitric acid. Is that a strong acid or a weak acid? Strong. So how would you determine the pH for this acid?
Equal to the concentration.
Right, the concentration for HNO3, the concentration of HNO3 will be equal to the concentration of H plus, right? Which is equal to 0.10 M. So therefore the pH is equal to what? Minus log of 0.10. And what does that give? 1.00. 1.00. All right, so that's easy. Of course, the nitrous acid will not be as easy because it's weak, right? So what do we do to begin with? I-stable. So HNO2 dissociates to form H plus NO2 minus. So initially, what would be the concentration of HNO2? 0.10, and this would be 0, this would be 0. The change here would be minus X plus X plus X, all right? And then at equilibrium, you're gonna have 0.10 minus X, here you're gonna have X, here you're gonna have X. What next? AA would be equal to
X squared.
X squared over 0.10 minus X, all right? What next?
You assume that,
Assume
0 plus X is equal to,
not equal to,
or approximate.
Less.
when I say that, 0.10 would be much greater than X, which means that 0.10 minus X would be approximately equal to 0.10, right? So this simplifies this equation to Ka is equal to X squared over 0.10. So therefore, X would be equal to the square root of 0.10 times Ka. So this would be equal to the square root of 0.10 times 4.5 times 10 to the minus 5. So 0.1 times 4.5 times 10 to the minus 5. And then we find the square root of that. And according to my calculation, I got rounded off to 2 sig figs, 2.1 times 10 to the minus 3. What next?
Hydrogen concentration.
Okay, but before you do that,
Then this is.
you have to find the percent dissociation because you have to make sure that the assumption you made earlier is valid. So how do we calculate the percent dissociation in this case? 2.1 times 10 to the minus 3
Initial constant.
over 0.10. So these are both M and M times 100%. And what are we looking for?
Less than 5%.
We're looking for this to be less than 5%. And according to my calculation, this works out to 2.1%, which is less than 5%, which means that the assumption is valid. And therefore, as somebody over here was saying, we can say that the concentration of H plus is equal to 2.1 times 10 to the minus 3 M. So therefore, the pH is equal to what? Minus log of 2.1 times 10 to the minus 3. So let's see what that gives. 2.1 times 10 to the minus 3. Find the log of that, remove the minus sign. Okay, so 2 sig figs, which means that this should be 2 decimal places. So this should be, according to my calculations, 2.68. And that's how that is done. All right? Any questions? Any questions? So obviously, same molarity, right? But different acids. One is strong, one is weak. The strong one has a pH of 1.0. The weak one has a pH of 2.68. So that shows you the difference in terms of the acidity of those two acids we're comparing. All right? Any questions? Yes, sir.
Instead of 2.1 times 10 to the minus 3, can I express it as 0.0021?
Yep, no problem there. Okay, any other questions about this? Any other questions? Okay, but I take it I can clear this. So let me clear this and scroll down. Okay, in the case of B, it's pretty much the same thing. The only difference, of course, is that we're dealing with bases, all right? We're dealing with 0.02 M potassium hydroxide and 0.10 M ammonium hydroxide, right? So, of course, you should recognize, oh, and another thing I should mention too, let me go back to the previous part. And I think I mentioned it to some students I was talking to earlier. If you see a question where they give you the Ka value, that's basically cluing you in as to the fact that it's a weak acid, right? So even if you are not sure, if they give you the Ka value for the acid, it's a weak acid. If they give you the Kb value for a base, it's a weak base. So that's another thing you can look out for when you're answering these questions. All right, so in the case of the B part, the potassium hydroxide is a strong base. The 0.10 M ammonium hydroxide is a weak base. So let's deal with the strong base first. How would you find the pH of the potassium hydroxide?
So that's equal to the concentration of H.
Okay, so the concentration of KOH is equal to the concentration of OH minus, which is equal to 0.02 M. So how do we find the pH from here?
Minus log H.
Minus log of the concentration of OH, which is 0.02, and that gives you what?
Seven.
1.7, yeah. Now, please note, what you're calculating here is a POH, right? So how do we find the pH? 14.00 minus 1.7 to give you 12.3, and that's it. That's how you determine the pH of that solution. So again, this is relatively easy. Now, what about for the ammonium hydroxide? What's the first step?
Weak.
Yeah, the weak base, yeah. So what do we do with this? What's the first step? Stable. So initially, you're gonna have 0.10. Here you're gonna have 0, here you're gonna have 0. The change will be minus x plus x plus x. And then at equilibrium, you're gonna have 0.10 minus x. Here you're gonna have x and x. So here now, we're gonna write down a Kb expression. Remember, it's a base, so therefore it's Kb that we'll be using. That is equal to the concentration of NH4 plus times the concentration of OH minus divided by the concentration of NH4OH. And then we put the numbers in, all right? Or the, not numbers, but the terms here. So when you do that, you're gonna end up with x squared over 0.10 minus x equals to Kb. And we can simplify this because we can assume that x is much smaller compared to 0.10, such that 0.10 minus x is approximately 0.10, and therefore Kb would be equal to x squared over 0.10. So therefore x would be equal to the square root of Kb times 0.10, which is equal to the square root of 1.8 times 10 to the minus 5 times 0.10. So let's do that here, 1.8 times 10 to the minus 5 times 0.1, and then find the square root. And according to my calculation, I got rounded to 2 sig figs, 1.3 times 10 to the minus 3, and that would be x. And that x would be equal to the concentration of OH minus, right? So what's the next step? I'm gonna need some more space. Let me erase here. What will be the next step? Now that we have determined the concentration of OH minus, the next step would be what? I'm sorry? Percent dissociation. How do we calculate the percent dissociation in this case?
Concentration of OH.
Okay, which is 1.3 times 10 to the minus 3 M divided by 0.1 M, 0.10 M, I'm sorry, times 100%. So that would be 1.3 times 10 to the minus 3 divided by 0.1 times 100. And according to my calculation, that works out to be 1.3%. And then what?
Less than 5, so that you can use.
Right, less than 5, so that means that the approximation is okay. Then what?
Then plug it into the POA and P.
Okay, so POH is equal to what? Minus log of
1.3 times 10.
1.3 times 10 to the minus 3. Let's see what that gives. Minus log, okay, so we have 2 sig figs, so this should be 2 decimal places. So I got 2.89 as a POH. And then what?
Subtract that.
So pH is equal to 14.00 minus 2.89. And according to my calculation, this works out to be 11.11. And that would be the pH. All right. Any questions about this one? Any questions? Any questions? Okay. I take it I can clear this. Let me scroll down. Okay, I think, did we answer this one? Okay. Did we do that one? Okay. And did I do this one?
Let's do a.
Oh, I said that you should do A, right? Skip B and C and do D. Okay, all right. So let's see what you guys came up with for this one. It says calculate the pH of the following solution. It's pretty similar to what we just did a while ago, right? So I'm just going to do the A part and in fact, hold on, let me see here. Let me see what B is all about. Oh, okay, all right. I'm going to do B and C with you guys, but let's quickly go through A. Let's see what you guys try to do with A, all right? So first step. What's the first step?
Five is a weak, strong.
All right, so what type of acid is this? Weak, okay, very good. What's the next step?
Acid.
Okay, so HClO, the form H plus ClO minus. So initially, you're gonna have 0.20 here, 0 here, 0 here. The change would be minus X plus X plus X. So at equilibrium, you're gonna have 0.20 minus X. Here you're gonna have X, here you're gonna have X. And Ka would be equal to X squared over 0.20 minus X. Then we're going to say that X is so much smaller compared to 0.20, such that 0.20 minus X is approximately X. So this simplifies to Ka being equal to X squared over 0.20, which means that X is equal to the square root of Ka times 0.20. So X would be equal to what's Ka? 3.2 times 10 to the minus 8, multiply by 0.2, and whatever you get there, we find the square root of all that. So let's see, 3.2 times 10 to the minus 8 times 0.2, and then find the square root. So according to my calculations, and please correct me if I'm wrong, but I got 8.0 times 10 to the minus 5. Right? The next step would be what? Percent dissociation. All right, so that would be equal to what?
8 times 10 to the negative 5 over 0.20.
Over 0.20, M times 100%. So let's see here, 8 times 10 to the minus 5 divided by 0.2 times 100. So according to my calculation, this is 0.040%, which is definitely less than 5%. So therefore, that assumption is okay. So what's the next step?
Concentration in pH equals negative log.
So pH is equal to minus log of 8.0 times 10 to the minus 5. So 8.0 times 10 to the minus 5, find the log of that, and then put a minus sign. Okay, so the answer I got, and again, please correct me if I'm wrong. You have to round this off to two decimal places. So this is going to be 4.10. All right, that's what I got. All right. Any questions? Questions? Okay, so let me do B for you guys. Let me clear this here. And let's do B. Now, B is a bit different from other type of questions of this type. Because now you're dealing with a salt. And we just talked about it. We just talked about salts just now. That's the reason why I couldn't tell you guys to attempt this, because I don't think you guys would succeed. So basically what's going to happen is that you're going to start off with this salt here, sodium cyanide, right? What will happen is that the sodium cyanide will dissolve in water and undergo complete dissociation to form Na plus Cn minus. Keep making that mistake. Right? So if you remember what I discussed when I was talking about, the acidity or basicity of salt, remember I said that after the dissociation, you have to figure out how will the ions interact with water, right? And if you remember, I said that in the case of sodium ions, they will not have any effect on water, right? So any change in the pH will not be due to the sodium ions present. However, the cyanide ion is a conjugate base of a weak acid, right? So this will interact with the water according to this equation. It's a conjugate base, so it's going to be a basic, right? To form HCN plus OH minus. So therefore, because of the formation of the hydroxide ion in this aqueous solution, this solution is going to be basic, right? So therefore, after solving the problem, if you get an answer which suggests that it's acidic, your answer is wrong, right? Because we already know from the outset that the solution is basic. So what we're going to do now is set up an ice table where initially you're going to have 0.055. Here you're going to have 0, here you're going to have 0. You don't need to worry about the water, all right? The change here would be minus x here, plus x here, plus x here, right? So at equilibrium, you're going to have 0.055 minus x. Here you're going to have x, here you're going to have x, all right? So up here now, I'm going to write down the Kb expression for this system, which is Kb is equal to the concentration of HCN times the concentration of OH minus divided by the concentration of Cn minus. All right? Now, we plug in these terms into this expression. You're going to end up with x squared over 0.055 minus x. And that will be equal to Kb. And again, just like before, we make an assumption. We assume, in this case, that 0.055 is much greater than x, such that 0.055 minus x is approximately equal to 0.055. So that will simplify the Kb expression to x squared over 0.055, which means that x will be equal to the square root of Kb times 0.055. And here's the trick now. Here's a little bit of a wrinkle in solving this. We do not know what the Kb is because they gave you the Ka for HCN, right? So we're not told directly what the Kb is. However, you can determine what the Kb is. So can anybody tell me how to determine Kb based on the Ka value? Yes, sir.
The 1.0 times 10 to the 14 and subtract it by that? Yeah.
Not subtract. Nope. Let me ask you this. Remember what the relationship between Kb and Ka is? You guys who came and saw me, you should be able to tell me because I told you when you were in my office. What's the relationship between Kb and Ka?
Thing where you're like Ka times Kb equals Kw.
Exactly, right? Remember this, folks. Ka times Kb is equal to Kw, right? So even though we don't know what the Kb is, we know what the Ka is, right? So therefore, what I'm going to do here is I'm gonna put where KB is, KW divided by KA times 0.055, right? And then I put the numbers in. So let me continue here. So square root of KW, which is 1.0 times 10 to the minus 14, divided by KA, which is 4.9 times 10 to the minus 10. And then we multiply that by 0.055. So let's see what that gives. 1 times 10 to the minus 14 times 0.055 divided by 4.9 times 10 to the minus 10. And then we find the square root of all that. And according to my calculation, rounded off to 2 sig figs, the answer is going to be 1.06 times 10 to the minus 3 m. All right? So that is x. Okay, so please note, if you're not given a KB, and this is usually the case when you're dealing with salts, if you're not given a KB for the conjugate base, you can use the Ka for the corresponding acid to determine KB by using this equation right here, right? Okay, we're not finished yet because we need to find the pH. So what's the next step?
The 1.06, I thought this was to be 2 significant figures.
Oh, yeah, you're right. Right, yeah, 1.1, sorry. So this should be 1.1. Thank you. Okay, what's the next step?
Where do we get 1.0 times 10 to the negative? Is that,
What I got on my calculator, you're talking about this here?
KW.
no, the KW?
Oh, 1.0 times 10 to the minus, that's a constant. Yeah, that's the ionic product of water. We made that 2 classes ago. And that is provided in that packet which you'll have available during your test, all right? Did I tell you about the table with the Ka values? Okay, so that you get that as well during the test, right? And I think that table also contains Kb values for certain bases. All right. Next step.
We calculate for percent dissociation.
Percent dissociation. How do we calculate that? 1.1 times 10 to the minus 3 m over 0.055 m times 100%. Let's see what that gives. 1.1 times 10 to the minus 3 divided by 0.055 times 100. And I got 2% or 2.0 to be more specific, which obviously is less than 5%. Okay, so that means that assumption is okay, all right? So next step, let me erase some of the stuff up top here. What's the next step? Find what?
The H concentration.
But before we do that, we need to find what? We need to find the pOH. So the pOH would be equal to what? Because remember, this is the concentration of OH minus, right? So pOH is equal to what? Minus log of 1.1 times 10 to the minus 3, right? So 1.1 times 10 to the minus 3 log. Okay, so I got 2. Okay, I have to round this off to 2 decimal places. So that would be 2.96. All right? But we're not finished yet. We need to find the pH. So how do we find the pH? 14.00 minus 2.96. And I got 11.04 as the final answer. All right? Any questions about this one? Any questions? Questions? Yes, sir.
So, how are we changing the we know that, we're in NaCN into the Na plus, Cn?
You're talking about this here?
Yeah.
Right, so sodium, any sodium salt, when added to water, will dissociate. And that's true for not only sodium, but pretty much all group 1 metal salts, sodium, potassium, lithium. So we know that that dissociation would have to take place first. And then now we have to ask ourselves, okay, how will the sodium and the cyanide affect water? How does it react with water? As far as the sodium is concerned, that does not react with the water, right? So there's no change in the pH due to the presence of the sodium. But the cyanide ion, because it is formed from a weak acid, right, which is hydrocyanic acid, the cyanide ion will react with water as a base, right? Because the cyanide ion is a conjugate base of the hydrocyanic acid, right? So therefore, we have two equations. The first equation would be this right here, and the second equation is where the cyanide will react with water to form OH minus, right? And HCN. And it is the OH minus that makes the solution basic, all right? And of course, that is confirmed by the fact that the pH that we calculated ultimately is 11.04, which of course means that the solution is basic, all right? Okay, any other questions? Any other questions? Okay, so let me clear this. Let me scroll down to C. Okay, now C is kind of similar, excepting that we're talking about an acidic salt. So let me go through this particular problem. Again, there are two dissociations that you have to take into account. The first one is the dissociation of the ammonium chloride. So NH4, Cl, dissociate completely to form NH4 plus Cl minus, all right? Then we have to ask ourselves the question again, how do these ions react with water? Remember we said that the chloride ion is very stable and therefore will not react with water. And the reason why that is so is because the chloride ion is the conjugate base of a very strong acid, which is hydrochloric acid, right? So if hydrochloric acid is strong, that means that the chloride ion, the conjugate base, is very weak, right? So therefore there'll be no reaction that would take place between the chloride ion and water. On the other hand, the ammonium ion here is formed from a weak base. So therefore, this will dissociate to form NH3 plus H plus, right? So basically, we're going to set up an ice table just like we did before. We're going to have 0.35 here, 0 here, 0 here. The change is minus X here, plus X here, plus X. And then at equilibrium, equilibrium, you're going to have 0.35 minus X. Here you're going to have X, here you're going to have X. And therefore, we can write down the Ka expression because this is acting as an acid. That would be equal to X squared over 0.35 minus X. We assume that X is much less than 0.35. So therefore, this simplifies to Ka is equal to X squared over 0.35. And then we find X, which is equal to the square root of Ka times 0.35, which is equal to, oh, again, here is a little bit of a wrinkle because now we have Ka here for the ammonium, but we have Kb for the ammonium, right? So what do we do here? Keeping in mind, we faced a similar situation in the previous question. What would you replace Ka with? Kw divided by Kb, exactly. So when we put those numbers in, let me do this over here. X will work out to be equal to square root of 1.00 times 10 to the minus 14 divided by Kb, which is 1.8 times 10 to the minus 5, multiply by 0.35, and then we work that out. 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5 times 0.35, and then I find the square root. Okay, so according to my calculation, rounded off to 2 sig figs, the answer should be 1.4 times 10 to the minus 5. Please correct me if I'm wrong, but that's what I got, all right? Okay, so that now would be equal to the concentration of H plus. So what's the next step? Percent dissociation. How do we calculate that?
The, is it the 1.4 times 10 to the negative 5? 0.35 times.
Okay, very good. 0.35 m times 100%, of course. So let's see what that gives. 1.4 times 10 to the minus 5 divided by 0.35 and then times 100. And according to my calculation, this works out to be equal to 4.0 times 10 to the minus 3%, which is obviously less than 5%. So that means that the assumption is okay. So, next step. Now that we know that the assumption is okay, that means that we can work with this, right? So what's the next step? Exactly. Let me squeeze that here. We're going to find a pH, which would be equal to minus log of the 1.4 times 10 to the minus 5. And let's see what that gives. 1.4 times 10 to the minus 5. Find the minus log of that. So according to my calculation, rounded off to 2 decimal places, that's going to give you 4.85. And that's how that is done. All right. Any questions about this one? Any questions? Questions?
That's 4.85.
4.85. Yes, ma'am. Any questions about this one?
So NH4, that's the
NH4 plus. You're talking about this here, right?
the NH4 CL.
Oh, up here, okay.
The NH4 is gonna be the weak,
The NH4 plus would be from a weak base, right? The NH4 plus is the conjugate acid of the weak base, which is ammonia, all right? So that is what undergoes dissociation here to form the conjugate base, the base which is weak, all right?
CL is from a.
The Cl minus is from a strong acid. And for that reason, the Cl minus does not react with water. If the acid is strong, that means the base is weak, right? And hydrochloric acid is as strong an acid as you can get, right? Which means that the base will simply not react with water to form anything basic. So we don't take that into account when we're calculating the pH.
So like for B then, with NaCN, Na is gonna represent the base that we're
The
gonna.
Na would be, the Na plus would be a very weak acid. It's stable. It does not react with water. The Cn minus would be the base. And it's a base of the conjugate acid, which is hydrocyanic acid, HCN. All right? Okay, any other questions? Any other questions about this one? So I take it it's okay for me to clear this, right? Okay. So for this one, D, again, there are 2 reactions that you have to concern yourselves with. The first one is the complete dissociation. NH4, OH dissociates to form NH4 plus, 4 plus, plus OH minus, right? Actually, this is not, I'm sorry, this is not a complete dissociation. Erase that here. Let me place this down here. So basically, this would be a partial dissociation. NH4, OH, because it's a weak base. To give you NH4 plus, plus OH minus, right? So basically, it's, we set up a nice table. It should be OH minus. The change here would be minus X plus X plus X. At equilibrium, you're gonna have 0.50 minus X. You're gonna have X here. KB would be equal to the concentration of NH4 plus times the concentration of OH minus divided by a concentration of NH4OH, which would be equal to X squared over 0.50 minus X. And then we make the assumption as usual. We assume that X is much less than 0.50, which means that 0.50 minus X is approximately 0.50. And then down here, that simplifies to KB is equal to X squared over 0.050 minus, okay, 0.50 minus X. Don't need X anymore. So this implies that X is equal to the square root of KB times 0.50. So that's square root of KB, which is 1.8 times 10 to the minus 5 times 0.50. What's 0.50? Goes here. And then we do the number crunching. 1.8 times 10 to the minus 5. 1.8 times 10 to the minus 5 times 0.5. Then we do the square root thing. And I got, and again, please correct me if I'm wrong, I got 2 sig figs 3.0 times 10 to the minus 3, right? What's the next step?
Dissociation percent.
Hmm?
The percentage dissociation.
So percent dissociation would be equal to what?
Point.
3.0 times 10 to the minus 3 m divided by
0.5.
0.50 m times 100%. And I'm quite confident this is less than 5%. 0.6%, which is less than 5%. So this is okay. So what's the next step?
Use the POH.
Okay, so POH is equal to minus log of 3.0 times 10 to the minus 3. So 3 times 10 to the minus 3 log. So I got, rounded out to 2 decimal places, 2.52. What next?
14.00 minus 2.52.
To find the pH, right?
Yes.
So pH is equal to 14.00 minus 2.52. And I got 11.48 as the answer. Yes, ma'am.
Now, when you're like getting the answer for the POH, how comes it's 3 sig figs now instead of,
Where? You mean here?
yeah,
Because remember we said whenever you do the log, whatever the number of sig figs here, the number of decimal places must be the same. So since you have 2 sig figs here for 3.0, when you apply the log, then the answer must be rounded off to 2 decimal places. Whatever the number of sig figs in the number that you're doing the log of, the number of decimal places in the answer would be the same. All right? Okay, any other questions? Any other questions? Okay, can I clear this? And let me scroll down. Okay. Did I tell you guys you should be able to do this? Okay, this one is relatively simple actually. It's asking for the pH of a solution and it gives the molarity of the weak acid. And it says that it's 2.2% ionized. So the equation you're going to use in this question is the percent ionization or percent dissociation equation, which is equal to the concentration of H plus times the initial concentration of the acid, HA, initial, times 100%, all right? So they gave you the initial concentration of the acid, and they gave you the percent dissociation. And the question is asking for the pH. So basically, we can rearrange this equation to get the concentration of H plus equals to the initial concentration of HA times the percent dissociation divided by 100%. So that would be 0.25 m multiplied by 2.2% divided by 100%. And that would give 25 times 2.2 equals divided by 100. So that gives you 0.55. So therefore the pH is equal to what? Minus log of 0.55. So this has to be rounded off to 2 decimal places. Let me just check something here. 0.25. Oh, I did something wrong. Okay. 0.25 times 2.2. Oh, wait a minute.
It's supposed to be 0.0055 m.
Yes, it should be 5.5 times 10 to the minus 3. Okay, so now we need to find a log of 5.5 times 10 to the minus 3. And when I do that, I got, and again, correct me if I'm wrong, but I got 2.26 as the answer. All right? Questions about this one? Yes, sir.
Because the percent dissociation of 2.2%,
Mhm.
that since it's less than 5, we just use 0.25 to equal to the.
No, 0.25 is the molarity. That's something different. That's not a percentage. The 0.25 in this question is the molarity, the initial molarity of the acid. This is the percent dissociation. You see what I'm saying? Yeah, this is the percent dissociation. They gave you that already. What the question is asking for is a pH. Where we can find a pH, we need to find the concentration of H plus. You see what I'm saying?
Yeah.
So that's why I arrange this equation like this, plug the numbers in, get the pH. I'm sorry, get the H plus concentration and then get the pH. Okay, any other questions about this one? Any other questions? All right, let me clear this. Scroll down. Okay, that's a repeat, ignore that. Okay, now this one is going to be very long. It says, find the pH of a solution that contains 0.0034 m lactic acid, and it gives you the Ka value. And also in that mixture, you're gonna have 0.056 m propanoic acid, and it gives the Ka value, right? So the approach that you take in the case of this question is that you're going to find the concentration of H plus that is contributed by each acid, right? So you have to go through the same steps that we did in the previous problems where you find the pH for one acid. In this case, you have 2 acids, right? So you have to find the concentration of H plus formed from the lactic acid, and then do the same thing for the propanoic acid, and then you add them together to get the total concentration of H plus, and then you find the pH, which will be the minus log of that value, right? So that's just an overall description of how that will be done. So let me start off with the calculation for the lactic acid. So I'm going to say here for lactic acid, I'm going to set up an ice table. I'm just going to use HA to get H plus A minus. And then initially, the concentration of the lactic acid will be 0.0034. This will be 0, that will be 0. And the change here will be minus X, plus X, plus X. And at equilibrium, you're going to have 0.0034 minus X. Here you're going to have X, here you're going to have X. Ka is going to be equal to X squared over 0.0034 minus X. And of course, we assume that X is much less than 0.0034. So that means that 0.0034 minus X is approximately equal to 0.0034. So that simplifies this equation to give Ka is equal to X squared over 0.0034, which means that X will be equal to the square root of Ka times 0.0034. So Ka is equal to 1.4 times 10 to the minus 4 multiplied by 0.0034. And let's see what that gives. 1.4 times 10 to the minus 4 times 0.0034. And then we find the square root. So according to my calculations, the square root of that gives you 6.9 times 10 to the minus 4. All right? So what's the next step? Percent dissociation. How do we calculate that in this case? 6.9 times 10 to the minus 4 divided by 0.0034 m times 100%. So let's see here, 6.9 times 10 to the minus 4 divided by 0.0034 times 100. And guess what? Percent dissociation is 20%, which is obviously greater than 5%. So what does that mean? We have to come back to basically this equation right here and solve it the longer way, all right? So let me create some space here. Okay, so I'm just going to rewrite this equation here. Ka is equal to X squared over 0.0034 minus X, right? And Ka is equal to 1.4 times 10 to the minus 4. So we have to cross multiply. You're going to get X squared is equal to 1.4 times 10 to the minus 4 times 0.0034 minus X. And then we have to distribute that. Okay, so 1.4 times 10 to the minus 4 times 0.0034. So this part here, when you multiply this by this, you're going to get 4.76 times 10 to the minus 7. And then this times minus X gives minus 1.4 times 10 to the minus 4 X. And that is equal to X squared, right? And then now we have to move 4.76 times 10 to the minus 7 on the other side. So the way we do that is that we subtract 4.76 times 10 to the minus 7 from both sides. And then we add 1.4 times 10 to the minus 4x to both sides. So that these two will go, so you're gonna end up with 0 on this side. And here you're gonna end up with x squared minus 4.7, I'm sorry, plus plus 4.76 times 10 to the minus. Come on. What I meant to say is 1.4 plus 1.4 times 10 to the minus 4 x minus 4.76 times 10 to the minus 7. All right, so this is minus 4, that's minus 7. So basically we need to solve this quadratic equation. And as I was telling I'm sorry, yes, sir.
You do the 0.0034 times 1.4 times 10 to the power negative 4. Do you not need 2 sig figs or?
Oh, sig figs, yeah, you're right. So let me correct that here. So this should be 4.8. So this should be 4.8, and this should be 4.8 here, which means that here you should have 4.8. Okay, thank you. Okay, so as I was telling some students this morning, I would strongly recommend, and I think I told you guys this yesterday too, that you have access to your fancy, what do you call it, TI-83 or whatever that calculator is, because you can program it to solve quadratic equations, right? Once you program it, all you have to do is put the A, B, and C value into your calculator and press execute, and that's how you get that. So please do that. I would strongly recommend that because you don't want to be, I'm quite sure you don't want to be during your test trying to use the quadratic formula, right? That will be more tedious. Now, what I'm going to do here is that I'm going to use a quadratic formula calculator. Okay, let's see here. So what I'm going to do now is input the A, B, and C value. Now the A value is 1. All right, the B value is 1.4 times 10 to the minus 4. So that's the same thing as 0.00014. And then for the C value, that would be 4.8 times 10 to the minus 7. So that's 0.1, 2, 3, 4, 5, 6 zeros, then 4, 8. Okay. Let me check just to make sure that is correct.
That C value is supposed to be negative.
And it should be negative, yes. And okay, so calculate. And let's see the results. The results are, okay, so these are the two values of x. Of course, the one that we're going to use is the positive value, which is 1, 2, 3, 4. So that would be 6.2 times 10 to the minus 4. So
Wouldn't it be 6.3?
6.3 times 10 to the minus 4. Yeah, thank you. So x would be equal to 6.3 times 10 to the minus 4. Okay, so let me get out of that and go back to this. All right, so this is what x is going to be equal to. Right here, 6.3 times 10 to the minus 4. All right, so that's for one acid, right? So this would be the concentration of H3O plus for the lactic acid. So believe it or not, we have to do basically the same thing for the other acid, which is the propanoic acid, all right? But I want us to keep this in mind. In fact, make sure you record this because you're gonna need this later on. I'm going to erase it, but make sure you keep this value handy, all right? So what I'm gonna do now is clear this, and then we're gonna do the same thing for the propanoic acid. So I'm going to jump the previous steps because basically it's the same thing. The only difference now is that the Ka value is going to be equal to x squared over 0.056 minus x, which means that this simplifies to x squared over 0.056, because again, we're assuming that x is much less than 0.056, right? And therefore, x will be equal to the square root of Ka. Oh, by the way, this is for the propanoic acid. So let me write that down just to make sure you know what we're working on. Okay, so x would be equal to Ka times 1.4. I'm sorry, 0.056. I'm sorry. 0.056, all right? So Ka is 1.4 times 10 to the minus 5, multiplied by 0.056, and then we find the square root of that. So let's see what that gives. 0.056 times 1.4 times 10 to the minus 5. And according to my calculation, oh, and square root, can't forget that. So according to my calculation, this works out to be 8.9 times 10 to the minus 4. Next step is to find the percent dissociation. And that will be equal to 8.9 times 10 to the minus 4 m divided by the initial concentration, which is 0.056, m times 100%. So let's see what that gives. 8.9 times 10 to the minus 4 divided by 0.056 times 100. And fortunately, this works out to be equal to 1.6%, which is less than 5%. So therefore, the assumption is okay. So that means that, what's the next step? Now that we know that the assumption is okay, what's the next step?
Find the pH.
Okay, how do you do that?
It's the negative log of
Minus log of
8.9.
8.9 times 10 to the minus 4. Because this is going to be the concentration of H0 plus produced by the propanoic acid. So 8.9 times 10 to the minus 4. Then we find a log of that and put a negative sign. So, oh no, before we do that, what do we need to do next? Exactly. So what was the previous hydronium ion concentration?
6.3 times 10 to the negative.
6.3 times 10 to the minus 4?
Yes.
Okay, so what we need to do is add this to this. So let's do that down here. 6.3 times 10 to the minus 4 m plus 8.9 times 10 to the minus 4 m. Let's see what that gives. 6.3 times 10 to the minus 4 plus 8.9 times 10 to the minus 4. Okay, so according to my calculation, this works out to be 1.52 times 10 to the minus 4 m, right? So now we can determine the pH. That'll be equal to minus log of 1.52 times 10 to the minus 4. So let's see what that gives. Log. Okay, so this is 3 sig figs, so you need 3 decimal places. So this is going to be 2.818. And that would be the answer. Yes, ma'am.
Curiosity, it might be wrong. So you're finding the when you're doing the 6.3 times 10 to the negative 4 plus 8.9 times 10 to the negative 4, you're just finding the new hydrogen concentration, right?
Right. That is produced by the propanoic acid.
Didn't you do it the same way if you just found the pH for both of them and just add them at the end, or is that
No,
something
not the
different?
pH. You can't add the pH there. You have to add the concentrations.
Oh, no, I see what you're saying.
Right. You add the concentrations. Then you find the minus log of that to get the pH. All right, yes, ma'am,
Would it be 15.2 times 10 to the minus 4
I'm sorry,
for the,
you mean here?
yeah,
You just add these two.
I got 15.2.
6.3 times 10 to the minus 4 plus 8.9 times 10 to the minus 4. I got 1.52 times 10 to the minus 3. Okay, this should be minus 3, my bad. Okay, so that changes this to minus 3. So this is not correct. So let me do that log. Oh, wait a minute. Hold on. 1.52 times 10 to the minus 3. Log of that. I got the same thing. 1.52 times 10 to the minus 3. I must have written it down wrong, but it's correct in the calculator. So the answer is still 2.18. 2.818, sorry. 2.818. So that's still the answer. It's just that I apparently wrote on the wrong thing earlier. Okay, any other questions? Yes, sir.
Add 6.3 and 8.9. That'd be 2 sig figs.
No, remember, when you're adding and or subtracting, you round off to the lowest number of decimal places. So what would happen if you add 6.3 to 8.9, right? You're gonna get 3 and 9, 12, 3 plus 9, 12, and then 15.2, right? Now this is times 10 to the minus 4, and this is times 10 to the minus 4, which means that this will be times 10 to the minus 4, right? Which works out to be 1.52 times 10 to the minus 3. All right? Okay, any other questions about this problem? Any other questions? All right. Let me clear this. Let me scroll down. Okay, so this question says you have vitamin C, which is the same thing as ascorbic acid. It gives you the formula here, and it says what is the pH of a 0.10 m solution, and what will be the concentration of this? Now, this is formed after this loses 2 protons. It gives you 2 Ka values, Ka1 and Ka2. Ka1 is for the first dissociation, and Ka2 is for the second dissociation. So again, what I'm going to do is I'm going to say let H2A represents this, right? Because the formulas of the compound is not really that important in terms of answering this question, right? So basically, you're going to have 2 dissociations. You're going to have firstly H2A dissociating to form H plus A minus, all right? So because they gave you Ka values, that tells you that both dissociations are weak. So therefore, we need 2 arrows here for the first dissociation, for which Ka1 is equal to 7.9 times 10 to the minus 5, right? So initially, we have 0.10 m of the H2A. Here we're going to have 0, here we're going to have 0. The change here is minus x for the H2A, plus x for the H plus x for the A minus. So at equilibrium, you're going to have 0.10 minus x. Here you're going to have x, here you're going to have x. So Ka1 would be equal to x squared over 0.10 minus x. Again, we assume that x is much less than 0.10. So therefore, 0.10 minus x is approximately 0.10. So therefore, this simplifies to x squared over 0.10 being equal to Ka1, which means that x would be equal to the square root of Ka1 times 0.10. So we put the Ka1 value where, which is 7.9 times 10 to the minus 5 times 0.10, and we work that out. 7.9 times 10 to the minus 5 times 0.1, and then we do square root. So according to my calculations, this works out to be equal to 2 suffix. So 2.8 times 10 to the minus 3 m, all right? Again, we do the percent dissociation, which would be equal to 2.8 times 10 to the minus 3 m divided by 0.10 m times 100%. So let's see what that gives. So according to my calculation, this works out to be equal to 2.8%, which is less than 5%. All right. So therefore, the assumption is okay. Now, you might be wondering, what about the second dissociation, right? Do we take that into account? And the simple answer is no. You know why? If the first dissociation is so weak, right, that means the second dissociation is even much weaker, right? So therefore, we do not have to take the second dissociation into account when determining the pH. So all we have to do from here is use this value for the concentration of H plus and find the pH. So the pH is equal to minus log of 2.8 times 10 to the minus 3. So let's see what this gives, 2.8 times 10 to the minus 3, and then we do the log. And according to my calculation, this works out to be equal to 2.55, round off to 2 decimal places. And that's how you do that. All right? Any questions? Any questions about this one?
So you put on the other ones.
Right, you don't take the second dissociation, you don't have to. You could if you want to, but that's a lot more work, all right? So you don't have to do that because the first dissociation is less than 5%. You see what I'm saying? And that's what happens in every any polyprotic acid, that's what I meant to say. That term, I don't know if I've explained that term before, but when we say an acid is polyprotic, it means that it has more than one hydrogen ion that it can release, right? So what you find in all of these acids is that the first one is the easiest one to release, right? Sometimes that's strong, such as sulfuric acid. And then what you find is that the second is weaker, the third one is weaker. So therefore the percent ionization decreases as you go from one dissociation to the other. So if the first one is less than 5%, then the others will be less than 5% for sure. All right? So that's why in this case, we don't need to take into consideration the other dissociation. Okay, any other questions before we move on to the second part? Yes, sir.
The second question is, what would be the concentration of?
We're going to get that first. We're going to get that next.
Oh.
Yeah, but I want to make sure that we understand what we did in the first part. Okay, so let me clear this. I think I'm going to need something from, I'll ask you guys anyway. So let me clear this. Now, for answering this question is asking for the concentration of A2 minus, all right? Now, in this case, we have to look at what happens when HA minus undergoes the dissociation here. What am I doing? Undergoes dissociation to form H plus A2 minus. Excuse me. And the Ka2 value is the equilibrium constant for that, which is the concentration of H plus times the concentration of A2 minus over the concentration of HA minus, all right? So we set up an ice table. Now, here's the thing. The ice table will contain values that were obtained from the previous equilibrium ice table. In fact, the final set of values in that previous equilibrium ice table would be the initial values that you're going to have here. So, since I erased it, I'm going to depend on you guys. What was the concentration of H plus that we got at the end? X. I'm sorry?
8 times 10 to the negative
10 to the minus what?
third.
3, okay. And what was the concentration of HA minus? At the end, the last line in that ice table. Oh, that was, what was that last line? What was in the last line for HA minus?
H2A.
No, but H2A dissociates to form H plus and HA minus.
You just wrote A.
Yeah, you just really.
You just.
Or it should be A minus. I'm sorry. But at the end, that last line, what was the value in that last line? Was it X?
Yeah.
Okay, and X is equal to the concentration of H plus, right? So we're gonna put that same value here, 2.8 times 10 to the minus 3. All right? Now, there'll be no A2 minus to begin with. So the change here would be minus X, and plus X here, right? So at equilibrium, you're gonna have 2.8 times 10 to the minus 3 minus X. Here, we're gonna have 2.8 times 10 to the minus 3 plus X. Here, we're gonna have X. Now, here's the thing. For the second dissociation, we can effectively assume that X is gonna be 0 here and here, right? Because again, the second dissociation is so small, right? So basically, you're gonna have 2.8 times 10 to the minus 3, 2.8 times 10 to the minus 3 as the equilibrium concentrations at this stage, right? So all we have to do from here is plug in these values into the equation where we have H plus here and HA minus, right? And what do we end up with? 2.8 times 10 to the minus 3 times concentration of A minus this should be A2 minus, I'm sorry. I'm messing up. Concentration of A2 minus divided by 2.8 times 10 to the minus 3 equals to Ka2. And guess what? Those two will cancel out each other, right? So basically Ka2 will be equal to the concentration of A2 minus, which is this, 1.6 times 10 to the minus 12. So that's the answer for the second part. All right? Yes, sir.
I should take out the X on the hydrogen ion concentration.
I mean here, because it's small,
Oh, yeah.
right? So therefore, the second dissociation will be smaller compared to the first dissociation. So the X value will be small. And you can go ahead and calculate the percent dissociation. You're going to see that it's going to be even less than what it was before, right? In the first dissociation. Yes, ma'am.
How did you get the exponent or for like A?
Oh, did I get what?
You put the exponent for A at the end. Why did you do that?
For A, oh, you mean this?
Yeah.
2, no, that's because the charge here is 2 minus. When HA loses a proton, the negative charge decreases from -1 to -2. So I'd forgotten to put that here in that equation. All right, any other questions about this? Any other questions? Yes, sir.
I know that H plus is gonna be 2.8 times 10
To the -3, yep.
How is HA minus also?
Because from the first dissociation, if you look at the last line in that ice table, the concentration of A minus and the concentration of HA minus and H plus is X from the first dissociation. So whatever the concentration of H plus is, the concentration of HA minus would be the same.
On the ice table, did you actually mean to write H2A dissociated to H plus and then
Plus HA minus.
HA minus
Yeah.
and A minus?
Right, not A minus, yeah. That's a mistake on my part. I'm sorry. Okay, okay, not much time left. So we need to decide if you want to, which day would be appropriate or which day would be convenient for you guys to link up via Zoom, if you have any questions and so on. Like I said, the only days I'll be available will be Friday and Sunday, not Saturday, all right? So when would be a good time, or which day would be a good day, or both days? Doesn't matter to me. Which day or days would be good for you guys?
Friday works.
Friday.
Friday? No Sunday? Well, if it's Friday, then what time would be convenient?
In the afternoon if
No
possible.
problem. What time will you have to? 3 until when? Suppose I say 3 to 7, is that fine? Are we in agreement with this, or most of us are in agreement with that? 3 to 7? All right, so I'm gonna make it Friday. I'm going to create the Zoom link for Friday, 3 p.m. to 7 p.m. All right? So feel free to come. By the way, let me see. Let me see something here. Because I don't think we're finished with this yet. Number 17. Okay, number 17 is the only one left, so we can look at that. And for those of you who can't make it, I'll just create a video of that meeting so that you can have it to look at. I'm gonna post it in Canvas. Okay, I think that's it. And I have a sneaking suspicion there's something I should be telling you guys, and I can't remember what it is. All right, that's it for today. If anything, I'll make an announcement later on. All right?
One second for, the next.
No. But I can publish it online in Canvas.
Okay, thank you.
Yeah, no problem. What's up?
We're gonna have the practice test for
Okay,
two. That's question.
right. That one is kind of similar to what we just did, excepting that the first association is strong.
Right, and, what's H3 O plus gonna be equal to the H2A?
Because if I were to set up the S table, it would be H2A forming H plus and A minus, right? So whatever the amount of H2A that you start off with, which is
Or would
what?
it be HA minus?
A minus, you're right. But whatever the amount of what's the concentration? So if this is 2.0 M, that means that this will be 2.0 M because the dissociation is strong. Complete dissociation. All the H2A will be converted to H plus. And that is different from the one that we did just now, because the one that we just did just now was I erased it, but
Was
the dissociation was weak. The first dissociation was weak, so we had,
weak acid or?
yeah, it was a weak acid.
The H2A is a strong acid.
That's gonna be good.
Well, this question says that the first dissociation complete, so that means the first dissociation is strong.
Yeah.
Oh, so when it says first dissociation complete, that's like 100%.
Exactly, 100% dissociation, so therefore, basically, whatever the molarity of the original acid is, the molarity of H plus would be the same.
For this,
Yeah.
this is exactly the same thing as, that's just another way of writing it.
Yeah, H3O plus. Now, the error here is that this should be a one directional arrow.
So I have to go
But
pinpoint
apart
and
from
see where
that,
that's at,
that
make sure.
basically-
That's what I did last time, just figured out. but
This-
it's not on the.
Right, this instead of.
Exactly, yeah,
That's, that'll be fine.
That's
No
what
problem.
I
Writing
did.
HA.
Exactly, no problem, same thing.
Doing this.
Yes, sir.
Yeah, I know, I only did. I have to do the rest of it.
I'd like to add to that thing.
Sure, yeah. So this week I'm gonna have to study for this and that at the same time, yeah.
I've done like half of 4.1.
Okay. Yeah, I did 4.1 and then 4.5 I did after he taught class, which was the infinity.
So what is that?
Infinity one.
I have this. I don't think.
Okay.
It's
Oh,
about,
it needs to be
it's
split
basically
like.
the same as doing the horizontal isotopes,
Let's
the
fit.
caltrate,
Oh, yeah.
so it was the same exactly,
That's-
so it wasn't that bad.
But, that's
Yeah,
That's right now. It's
Mhm.
easier.
yes. I think we have, after this, do we have another test here? Yeah. I think it was 3 times, so I don't think.
Yeah, everything else seems,
Are we on 4?
Looks
So
okay.
we have to learn 5. 5, there's not gonna be a test, but it's gonna be on the final exam.
Is that what you said?
Yeah. But I'm
yeah,
wondering if
but this,
he's like he was gonna test this.
I need a
the
point
inverse,
for each of those
trigonometric.
guys. I don't know, what did you use to create this?
Well, yeah, I thought you said it was gonna be on the next ones, but maybe he's.
I don't know, I'm not familiar with Google.
Also because.
Yeah.
That they get.
Mm-hmm.
So yes,
Yeah.
yes, like here's. Like,
Yeah,
it's
so I have to
like,
figure out
here's like
something.
0.5.
Are you-
Here's
No.
0.5.
No.
And the same distance is whole thing.
Yeah.
So when you graph it, it would be a straight.
It's not required.
But when,
So are you
because,
gonna do it eventually?
I think,
No, it's not
like,
required.
basically, if this was here,
Mhm.
That's nice.
I think that might be why.
No, I don't think that's the issue. The issue is that
That like 6:15.
Google Sheets,
How many days a week?
I think, should be able to
Yeah.
find the line of best fit between these 3 data points. I know that,
I mean, I can make a
2:30 to 6.
or yeah, you can draw a line, I mean, freehand.
The class it is.
But, yeah, I'll accept that. But the thing is that, what's the other one? Excel. You should be able to do that, in Excel as well, but I'm not familiar with the Google Sheets.
But if I draw the line of best fit, it should.
Yeah, I'll take it, yeah.
And then for the questions I was asking about it, like what the relationship is, would I say linear?
What's the question? What is the question asking?
Describe the mathematical relationship between reaction rate and temperature in kelvins.
Yeah, you say linear too, yeah.
Linear?
Mhm. Okay, yes, sir.
Test this tomorrow.
What's that?
Test this tomorrow.
No, it's not tomorrow. I don't know if you saw the announcement I posted.
That's what I.
So I put it over until Monday,
Oh,
right? So that,
So what do
you
you
guys
tell-
have more time. And it's gonna be based on this chapter and the previous chapter. Acid bases and,
So
equilibrium.
you said.
Yes, ma'am.
I mean, I got.
Yeah, and then it's.
Oh, you could. Line of best fit. He just said to draw a line.
Yeah, do you?
Oh, like a straight line? Yeah, can you show me?
Yeah,
So
You get a straight line? Yeah. It's almost exactly.
No, you have to do the second part because you're two dissociation. This here
It doesn't make any sense.
is for the first dissociation, which is the H plus. So because it's less than 5%, then we don't need to go back to here and solve it the longer way.
I used
You see what I'm saying? The reason why we assume that X is small is to simplify this equation so that it makes it easier for us to determine X. But if it was greater than 5%, then basically we have to go back here and solve for X the longer way.
I understand that.
Right.
Said if I.
This part here is for the second dissociation.
So it's a straight line.
Yes, ma'am.
Hopefully. And you know,